Continuing our survey of functional groups, we come to the carbonyl group, molecules that contain a carbon-oxygen double bond. The carbonyl group is arguably the most important functional group in all of organic chemistry because nearly all of the important biological molecules contain a carbonyl group somewhere in their structure. So here's a picture of a carbonyl group, a C double bond O, and then of course the carbonyl carbon, as we call it, can have two other groups bound to it. And I'm just going to give them the generic letters X and Y because we can further subclassify carbonyl groups depending on the identity of the groups X and Y. So you're going to need to know all of these other specific carbonyl group subclassifications. You have the aldehyde, the ketone, the carboxylic acid, the ester, and the amide. Okay, so an aldehyde is what you get when at least one of those two substituents, X or Y, is a hydrogen. If they are both hydrogens, this is a molecule called formaldehyde. Formaldehyde in the pure state is a gas. But you may be familiar from biology classes with aqueous solutions of formaldehyde, which are used as preservatives for specimens. If both X and Y are carbon, you have a ketone, and you probably have already been introduced to a ketone in the laboratory because acetone is the compound that you typically use to rinse out glassware in the organic lab, and it is the simplest ketone. Carboxylic acids are when the Y group is an OH, so that gives you the COOH functional group. And in this case, you can have a carboxylic acid with X being hydrogen or carbon. If X is hydrogen, you have formic acid, and if X is carbon, you have all of the other carboxylic acids. Esters are further derivatives of carboxylic acids, where instead of Y being OH, Y is OR. Okay, so a larger organic group on the oxygen side of the molecule. And then finally, amides are the functional groups in which you have Y equal to nitrogen. Now that nitrogen can have two hydrogens on it, one hydrogen and one carbon, or two carbons on it. I like to say that one analogy is that ether is to ester as amine is to amide. Okay, they are similar functional groups except the ester and the amide have a carbonyl next to the oxygen or the nitrogen respectively. A common mistake that students make is confusing ether and ester and confusing amine and amide. So you will need to learn to get those correct. Okay, some other nitrogen-containing functional groups. So we've now gotten through the organic chemistry of oxygen. Imines, also known by biologists to be Schiff bases, are compounds that contain carbon-nitrogen double bonds. Okay, so here is an example of an imine, and you can see the CN double bond here. The nitro group is another group that will come up frequently in organic chemistry. Okay, so the nitro group formally has the formula NO2. And you may have learned about the nitro group in your general chemistry course, but if you didn't, it's a group that is neutral overall. But in order to follow the formal charge rules, it has a positive charge on the nitrogen and a negative charge on one of the oxygens. And it also has two resonance structures. So we have the double bond to one oxygen and the single bond to the other. I could have just as easily put the single bond to the top oxygen with the minus charge and the double bond on the lower oxygen. And then finally, nitriles contain a CN triple bond. Okay, so similar to alkynes containing a CC triple bond, nitriles contain a CN triple bond. And of course, there is one additional substituent on the carbon and no additional substituents on the nitrogen. Three more functional groups that you should be aware of are what I call the compound functional groups. And a compound functional group is when two or more simple functional groups that are close enough to each other that they influence each other are present in the same molecule. So the three that you need to be aware of are amino acids, in which you have an amino group and a carboxylic acid bound to the same carbon. Okay, so the carbon that we're referring to is this central carbon here, and it has an NH2 on the left and a COOH on the right. Then we have hemiacetals, and that's what, again, when you have the central carbon containing both an alcohol and an ether. I want to stress that the alcohol and the ether have to be bound to the same carbon in order for it to be a hemiacetal. Otherwise, it is simply a molecule that contains an alcohol and an ether and doesn't get a special name. And as you'll see in later parts of the course, hemiacetals have special reactivity relative to ethers and ordinary alcohols. And then finally, along the same lines, an acetal is what you get when you have two ethers bound to the same carbon. And once again, they have to be bound to the same carbon in order to be called an acetal to impart the special reactivity that we'll see later in the course.